Here we have a concave spherical mirror and an object in front of the mirror. And we're going to find the image produced by this mirror. Remember, we usually draw an arrow to represent the object. The F here is the focal point of the mirror. So this distance is the focal length. And we sometimes also label 2F, which is twice the focal length from the mirror. First, we're going to use ray tracing to find the image produced by this mirror. To use ray tracing, we need to draw two rays. The first one I'm going to draw is a paraxial ray. The ray is going to start from the tip of the arrow and it's going to be parallel to the principal axis. It hits the mirror and it's going to get reflected and goes to where? A parallel ray from a ray that is parallel to the principal axis is going to get reflected and go to the focal point. So this ray is going to go this way through the focal point. So this goes to the focal point. The second ray we're going to draw is one that goes to the center of the mirror. So this one goes to the center of the mirror. And how do you think this ray is going to get reflected? The reflection has to follow the law of reflection, which means the angle of incidence has to equal to the angle of reflection. And this is the normal line to the mirror. Therefore, the reflection should follow the law of reflection. That means these two angles should be equal, which means this ray should be reflected symmetrically. Symmetrical to the principal axis. So this ray would go like this. And these two rays would meet right over here, and that's where the image is formed. Because this is the image of the tip of the arrow, so the image looks like this. Which means we get a bigger image and it is inverted. And because this image is formed by real light rays reaching here to form that image, this is what we call a real image, and this image is inverted. So it's a real inverted image. Another example of a real image would be when someone uses a projector to project an image on a screen. That image on the screen would be a real image, because that image is formed by real light rays getting there. Just like this image, it's formed by real light rays reaching here. It's not formed by the light ray extensions. Sometimes ray tracing is convenient to use to find the image. However, one would have to be very careful at drawing the rays. It can be a good idea to have an equation to use. So now we're going to derive a mirror equation. To derive the equation, we're going to use some similar triangles we have in these ray tracing diagrams. That's why the ray optics is also called geometrical optics. There are two sets of similar triangles we're going to use. This right triangle up here and this right triangle down here. We have the right angles over here, and these two angles are the same because of the law of reflection. So these two triangles, they are similar. The distance between the object and the mirror is called the object distance, and we're going to use d sub O for that. The distance between the image and the center of the mirror is the image distance. We're going to use the d sub I for that. And the height of the object is the h sub O. The height of the image is the h sub I. Because these two right triangles are similar, so the sides are proportional, which means HO over HI, this over that, would equal to DO divided by DI. Now let's look at the second set of similar triangles. We have a right triangle over here. And then there's another right triangle over here. Of course, this one is not exactly a right triangle, but if the spherical mirror is small enough, that means this part is almost perpendicular to the principal axis. So this is about a right triangle. So right angle here, and these opposite angles, they are same. So these two triangles are similar, which means HO, which is this side, HO equals to that. So HO over HI would equal to this distance divided by that. And this distance here is F. And the distance over here would equal to DI minus F, right? DI minus F would equal to this side over here. So I can say that HO over HI is this distance, F, over that distance, which is DI minus F. So first, I'm going to flip both sides of this equation. So it's DI over DO equals to the DI minus F divided by F. And this side can be simplified as DI over F minus 1, right? DI over F minus 1. Okay, and then I'm going to divide by DI on both sides. So I'm going to get 1 over DO, and divide by DI on this side, I get 1 over F minus 1 over DI. And then I can rearrange things a little bit. I get 1 over DO plus 1 over DI equals to 1 over F. And this is our mirror equation. So now let's try this problem. Suppose the focal length here is 10 centimeters. And I drew the object over here right in the middle between the F and the 2F, which means it's between 10 centimeters and 20 centimeters. So my DO right now is 15 centimeters. And since I want to locate the image, I'm going to find the DI. So I can use this equation. 1 over DO is 1 over 15 plus 1 over DI equals to 1 over 10. So 1 over DI would equal to 1/10 minus 1/15, which is 30, and then 3 minus 2. So it is 1 over 30, which means DI is 30 centimeters. And yes, this is 10 centimeters, 20 centimeters, 30 centimeters away. We have the image. It's 30 centimeters away from the mirror. And because of all these similar triangles, that means the farther away the image is formed, the bigger the image. See, the HO over HI equals to DO over DI. So the larger the DI, the larger the HI. So we have this thing called magnification. We use big M. That equals to the HI over HO, the height of the image divided by the height of the object. That means if the image is magnified, as in this case, the M would be a number that is bigger than 1. Actually, because this image is inverted, so we're going to say this magnification is negative because it's an inverted image. But it's going to be negative something that is bigger than 1, which means a number that is smaller than negative 1. Okay, so the magnification definition sees over here we have HI over HO would be DI over DO. But we're going to put in a negative sign just because this is an inverted image, so the magnification should be a negative number. And now we can find the magnification for this case. We have DI is 30 centimeters, so this will be negative 30 divided by the DO, which is 15. So the magnification would be negative 2. The negative means the image is inverted, and the 2 means the image is twice the size.